stoichiometry. A real stoichiometry problem would be something like this. You know, I'm not going to have a limiting reagent. I'm going to try to do this with stoichiometric quantities. With stoichiometric quantities, I put 0.200 moles here. Right? I'm going to put 0.100 moles here. I'm going to put 0 moles here and 0 moles here. And so I'm going to put 0.2 and 0.1. See what happens. Okay, you predict what the percent reaction is going to be. What do you think the percent reaction is going to be if it's stoichiometric like this? Do you think I'm going to get 64% reaction of the copper like I did in experiment 1? Actually, you know what? It doesn't. It's not 64% reaction. Even though you look at experiment 1, it's kind of similar, right? And so it seems like it should be 64%, but it turns out if we did experiment 4, it's different. And so the question is it impossible to predict stoichiometry for these types of equilibrium reactions when there's a competition between the forward and the reverse reaction? And so the thing that it is impossible right now because it just seems totally random, doesn't it? Totally random. And you could see this. In science, we try to visualize things in different ways. And then we visualize this graphically. You know, we look for patterns. Is there a blue, black, red, green pattern that you see? You know, do you see a red, green, blue, black pattern? No. So we try to look for patterns in reactivity. And when I look at this, I don't see any pattern, right? I mean, I would hope, if I saw a red, green, blue, black pattern, then I would have some faith that I can actually do some calculations, right? But sometimes, you know, in science, finding the pattern can be very difficult. Like, you know, for example, if somebody didn't tell you about the pattern of reactivity in the redox chart, that is, you know, all these oxidizers can oxidize all these metals, would you have figured that out by yourself? Yeah, I mean, given enough time, right? You might. Or you might not. You know, sometimes these patterns are very tricky to find, right? And so people started thinking, well, if there's no pattern here, maybe I'm missing it. Maybe I'm missing it. Maybe there's some kind of thing that's happening here that I'm not seeing. And so one of the things that people tried to do was to look for a pattern in these numbers, in the n numbers. So if we look at the equilibrium numbers here, you know, even though I don't see a pattern in the individual, you know, maybe there's a pattern in that set of numbers there. Here. And so when we look at these blue numbers here, do you see a pattern in those?
No.
No. But you know what chemists are good at doing is they're good at and scientists in general, they're good at taking these numbers and then trying to fit those to a mathematical pattern. Remember the lines of the hydrogen spectrum? Did you see a mathematical pattern when you looked at the lines of the hydrogen spectrum? Probably not, but did you know there's a simple mathematical pattern to it? And it's called what was it called? No. The simple pattern was that, you remember this, E is equal to R sub H, 1 over n final squared, minus 1 over n initial squared, where n is an integer from 1, you know. Something like that. Do you remember that? That's the mathematical pattern of the hydrogen lines in the spectrum. And so just like the mathematical pattern in the hydrogen lines, people started looking for a mathematical pattern here, trying to fit these numbers into a mathematical equation. That's what we normally do. In fact, the ideal gas law is just what we call an empirical equation. Empirical equation is where you take the experimental data and try to fit it to a mathematical pattern or equation, right? And so what we're going to do is we're going to try to come up with an empirical equation that describes these numbers here by trying to fit it in some mathematical pattern. Well, Well, to make a long story short, because it would just take too much time, right, to go through all the attempts at this, let's look at some of the mathematical patterns that people try to fit this with. And so the first mathematical pattern, they're probably much more than this, right? Because you're just looking for some kind of math that fits those numbers. And so probably a lot more. But anyway, the first mathematical pattern that people did was, let's take the ratio of the product concentration. Well, actually, this is jumping way ahead. First, probably we'll take the moles of copper and tin, you know, over the moles of copper 2 and tin 2. So copper 1 and tin 4, right? And no pattern emerged. And so if we take the moles of the product divided by the moles of the reactant, no mathematical. Okay, then they gave up with the moles. And then eventually they went to molarity. Well, what if we take the concentrations? And don't ask me why. Just people are just looking and they're just trying to take random guesses, you know? Like, well, anyway, you just try a whole bunch of different things. This is part of the exploration process of science, right? You know, and the thing is, this is why I say, you know, did you come up with a question? You know, when I hear about the scientific method, a lot of people say, oh, first you propose a question, you know, and then you come up with some hypothesis. Well, what would the question be here? The question would be, does it fit this mathematical pattern? And you try it, see, something like that. But for us, you know, for chemists, we just look for patterns. This is what we do. And so here, there's no pattern in the molarities here. Do you see experiment 1? The ratios are totally different, random. Okay, then we say, well, you know, copper reacts twice as fast as tin. So what if we double the copper concentrations on both sides, right? And then look.
You would say.
Random, right?
Same random as.
Yeah. Okay, but instead, what if we square the copper concentration? If we square the copper concentration, and then you're thinking, what the heck, square? Why would you square the copper? Have you ever heard of molar squared? You know, hey, can you make me a 6 molar squared sodium chloride solution? Is that even possible?
36 molar?
Have you ever heard of molar squared? No, it's physically ridiculous, right?
Yeah.
It's physically ridiculous, but when you're scraping for some kind of pattern and you tried everything, and it's the same thing. Like you know, I even though the blue LED, that was last year's Nobel Prize, but I was watching this video. It was very interesting about it. But you know, he was working. The blue LED guy was working with gallium nitride, and everybody said, no, you don't. Gallium nitride's not going to work because, you know, they grow the gallium nitride on sapphire, which is aluminum oxide, basically with some dopants in there, just alumina. And it's a mismatch in lattice, so there are lots of lattice defects. So they're saying, you got to keep the lattice defects under 10 to the third, or something like that. He was getting lattice defects above 10 to the ninth, you know, per cubic centimeter or something like that. And so everybody's saying, no, forget that. That's a dead-end path, you know. And it turned out that,
The lattice is made of.
yeah, all those defects were very important in the. Yeah, if it wasn't for those defects, the efficiency would be way, way down. So it turned out, well, anyway, so you're thinking, well, we aren't going to worry about this. You know, that's what some people get caught up, you know, when they're doing this redox method, they're getting caught up. You know, should, I got this question on Piazza, well, is nitrate a spectator? Should it be a spectator? Isn't nitrate very reactive as an oxidizer? Yes, it is, but don't worry about that. You just do the pattern. You just do the steps. And ignore all that stuff. Don't think about that. And so we aren't going to think about what the squared means. Who cares what a molar? The units are going to be very strange. Molar squared, molar cubed, right? But if molar cubed on the top, molar cubed, they end up canceling. But sometimes they don't. But anyway, take a look at this pattern. Does it work?
Yeah.
Yeah.
So that number, does that mean that copper is 1.5 times more likely to be favored, or that C?
No, we don't worry because you know what? this is the scientific method. The scientific method is you start off with observations and then you go to, no. You start off with observations. Observations are experiments, by the way. You start off with experiments, observations like this, and then you go to patterns, right? And then you figure out a mathematical equation that fits those patterns and you call it a law. And so when we're using the ideal gas law, which is just a mathematical function that fits the pattern, right? Did you worry about all these other things? What does that mean? What does this mean? Why is P times V? Why isn't it P and V? You know, why didn't you divide it by T? You know, did you start questioning all that stuff, or did you just use it? If you got caught up questioning all that stuff, would you even be able to do one simple ideal gas law calculation? No, you'd be thinking too much. You know, am I supposed to be dividing by volume here? Shouldn't I be multiplying by? No, you just follow the equation and you plug in the numbers. And you do it, right? Then, after you do enough of those, then you start going, I'm so tired of those calculations. I want to know, you know, a little bit more, right? And so you start to hypothesize about the theoretical stuff, right? And so at this point, we're just at this. We got a pattern. When does a pattern become a law? Huh? It's reproducible. It happens all the time. It's like ideal gas. That happens all the time, right? It's reproducible. And so let me make a long story short. So what they did was they tried this on a lot of different reactions, not just this one, but this one with different, like for example, 2. You know what the end result here was? It fit the pattern. And so if they do enough of these without exception, then they're going to call it the law of equilibrium. Even though they don't call it the law of equilibrium in our book, I'm going to call it the law of equilibrium because that's exactly what it is. Laws are typically empirical equations that fit our observations. And the question why is very important, but that's not what we ask now. And so this is very similar to doing ideal gas law calculations. You're given an equation, can you use it? Can you apply it? Do you have to tell me why? Tell me why theoretically P times V. What does P times V mean? A lot of people, you should know what P times V is. What is P times V? Pressure times volume, but what is it? It's energy, right? Energy. P times V is energy. Liters atmosphere or bar atmosphere is energy, joules, right? And so what's the connection there with nRT, And so do you ever explain that? No. You just learn how to do the math, right? Well, I'll tell you, the first 4 chapters is just this. The first 4 chapters, all we're doing is learning how to apply this mathematical equation to help us solve problems. We aren't going to worry about why it's squared at all. Not at all. We aren't going to worry about the units being all screwed up and being nonsensical. We're going to worry about that later, but what we found a pattern that works. Once we found a pattern that works, that's it.
That squared is definitely coming from the ratio,
Right. And so let me tell you what the mathematical pattern is. The mathematical pattern is this. So this would be the law of equilibrium. The law of equilibrium is, let's see if I have some more in here. Is if we have some generic equation, little a is the coefficient, a is the reactant, b plus ... This goes to little g plus h plus ... And so we have some kind of generic equilibrium reaction where there's some competition between forward and reverse reaction. Then what we see is that the pattern of the concentration of g raised to the little g times the concentration of h raised to little h, ... all the products here, divided by the reactants, the concentration of a raised to little a, b raised to little b, ... This is going to equal a constant. Okay, this constant we're going to give a name. We're going to call this K sub C. This is K sub C. It turns out that the pressures, if we're dealing with gases, the pressures also, pressure is directly proportional to concentration per gas, right? If we look at the pressure of an ideal gas, the pressure of an ideal gas is equal to nRT over V. What is N over V? N is moles, V is liters. And so the pressure is equal to the molarity times the factor RT, right? And so it turns out the pressures, they have this constant in here, but the pressure is going to behave the same way. P sub G raised to little g, P sub H raised to little h, dot, dot, dot. This is for gases, over P sub A raised to little a, P sub B raised to little b, dot, 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 is equal to a constant. Now, the constant may or may not be the same, but we're going to call it something different. We're going to call it Kp. And so this is the constant when we're dealing with concentrations. This is the constant when we're dealing with pressures, gas pressures. Now, let me tell you some more of the mathematical pattern, and then we'll try to apply this next. Turn this off. All right. So the mathematical pattern is this. If I look at Kp, Kp is going to equal Kc times the factor RT, right? The concentration is related to the pressure by RT. And then this is going to be RT raised to the delta N of gas. Have you seen delta N of gas before? Yeah. In other words, we can figure this out because, K, is that right? Kp is equal to Kc, yes. Right. We can figure that out based on this. Kp, pressure is equal to pressure of G raised to little g, etc. Pressure of A raised to little a. The pressure is equal to the molarity, right, of G times RT. This whole thing is going to be raised to little g power. And the pressure of A is equal to the concentration of A times RT raised to the A power, etc. And so it depends, it depends on if the RTs cancel each other out. That is, if I have the same number of moles of gas on the reactant side as the product side, then all the RTs will cancel out. If I have different number of moles of gas, let's say I'm going from 1 mole of gas to 3 moles of gas, then the RTs don't cancel out. And I have to factor those in. This is the other pattern. This is the pattern that's related to. And so all we're going to do is apply these patterns to make some predictions. And so the first thing, as far as the calculations go, is the first thing is, how do I get the pattern? How I get the pattern is I just have to take the equilibrium concentration. And so the first thing is doing a K calculation. So if I want to figure out what my constant is, right, then I need the equilibrium concentrations, that is, these N concentrations, and then just plug them into the equation. That's all I do. And so to get the equilibrium concentrations, do I have to measure all 4 concentrations here? To get the equilibrium concentrations, usually what people do is they just measure 1 or 2. Because do I really need all 4 because an experiment to measure that is quite a pain. And so if I only measure 2, could I figure out the other 2? Yeah, I could figure out the other 2 because atoms are neither created nor destroyed. In other words, how I figure out the other 2 is I do this. I call the change minus x, but this is 2x. If this is 2x, then this is going to be minus x. And then this change over here has got to be plus 2x and plus x, just as a variable. And therefore I can figure out what these are, right? But these are moles, not concentrations. Then I'd have to, does it work for moles? It works for moles if the liters, if the volume cancels out. That is, it works for moles over here if let's say I had 4, and you know, liters here, liters here, liters here, liters, they cancel. But if I have like this, A goes to G and H, then the liters aren't going to cancel out. Something like that. Okay, so one type of calculation is figuring out what K is. We'll look at that, but I want to go back to this problem here. Kelly.
Then, if the meters don't cancel out, what do you do from that case?
Then we have to do an extra step here. If we have moles here, we have to convert it into molar and then plug it into the equation, because this equation is not for moles. Moles doesn't fit the pattern. Molar does, or atmospheres or bars does, okay? And so we just got to make sure, even though the units are nonsensical, we got to make sure that we're doing it in the right unit.
The pressure one has to be atmospheres or bars.
Atmospheres or bars. Either one's fine. But the K is going to be different for atmosphere. Well, is it going to be different? No, it depends on what it is. So let's go back to this. If I started off with 0.200 moles and 0.100 moles and 0 moles and 0 moles, this is what we're going to call the initial amount. And the book is going to do it different ways. When should I convert it into molarity? Should I wait until the end to convert it into molarity, or should I convert it at the beginning into molarity? Because I need it in molarity, right, or atmospheres. And so should I wait until the end or convert it? Well, it depends on case by case, you know. Sometimes it's easier to convert it at the beginning. Sometimes it's easier to convert it at the end. Most of the time, it's easier to convert it at the beginning. And so, since most of the time it's easier to convert it at the beginning, I'm going to do all the problems converting it right at the beginning into molarity. And so, in order to convert these into molarity, what do I need? I need the volume. And so, you know what? I don't want to pick a complicated volume. I'm going to pick a volume that's easy. You know the volume I'm going to pick? 1 liter. And so let's just assume we have 1.00 liters. We keep it to 3 sig figs. And so, that's easy, because this is going to give me 0.200 molar, right? And this is going to give me 0.100 molar and 0 molar and 0 molar, right? Now I want to figure out what is the change and what am I going to end up with at the end of this reaction. I want to predict the stoichiometry. But I don't know how much I'm going to lose. So what I'm going to do is I'm just going to use a generic. We're going to call this minus 2x, right? We're going to call this minus x, this is molar, and we're going to call this plus 2x molar, plus x molar. Now this has to happen, otherwise atoms are created or destroyed, you know? And I got to keep that stoichiometry. I just don't know what the percent reaction is going to be yet, right? But, you know, how am I going to figure out what x is? How do I figure out what x is? I need the constant, you know, I need the ratio, what that number is at the end. And so what I did do here is I have 3 experiments. So actually, I turned this off, but I'll tell you what the numbers were. And so the number comes out to 1.48, you know, average those 3. And so I know that Kc for this is 1.48. And so this tells me what the end ratio has to be. Because Kc is going to equal this. It's going to equal, well, let's first figure it out. It's got to be the copper plus concentration squared, right, times the tin 4 concentration divided by the copper 2 plus concentration squared and the tin 2 concentration to the first. And so now I know that whatever reaction takes place, by the end of this reaction, these are all equilibrium. The equilibrium or the end concentrations have to have this ratio, 1.48. And so I got to figure out those. Well, you know what the equilibrium concentrations are going to be is here. Right? This is the equilibrium concentration of copper 2 plus. Well, I don't know what it is. Yeah, but we can figure it out. It's got to be 0.200, right? Minus 2x. That's it, molar. The tin-2 equilibrium concentration must be 0.100 minus x, molar. The copper 1 concentration must be 0 plus 2x, so we'll just call it 2x molar. And the tin 2 is 0 plus x, so it's just x molar. And so now we can figure out what x is by plugging it into this equation. And so the copper plus 1 concentration is what we call 2x. This is 2x quantity squared. And then the tin is x divided by the copper 2 concentration, which is 0.200 minus 2x, divided by the tin 2 concentration, which is 0.100 minus x. And this, oops, minus, I'm missing a square. Here's a square here.
Yep.
And this has got to equal 1.48. Are you guys good at algebra? Yeah?
Yeah.
All right, so solve it. No programmable calculators, please. You could use a standard calculator, but you have to solve it using a standard scientific calculator, a SAT approved calculator. Well, we're almost out of time, so you can take this home, solve it, and next time, tomorrow, tell me the answer. I'm sorry? Oh, that equation? Do you remember that equation? It's called the Rydberg equation. Yeah, and the R sub h is the Rydberg constant. Okay. Okay. Yeah, that's what it is. Familiar equation.